My name is Mohammed Alsharqawi. I'm an assistant professor at California State University, and I'm pleased to be here today presenting this research with my co-authors, Drs. Dabous and Zayed. Our research proposes an automated decision tool for long-term scheduling for maintenance, repair, and replacement strategies with an implementation of bridge infrastructure as a proof of concept.
In this paper, we will briefly recap.
Here's an outline of what I will be covering during this presentation. First, I'll introduce the research overview and literature background. Next, I will present the tool development framework and expand on performance modeling and components and optimizing MRR strategies. I'll then showcase the developed tool on a bridge infrastructure. At the end, I'll wrap up with the conclusion and future works.
Manual method like the hand tool is showing.
Deterioration is the foremost problem that affects the performance of bridges like any other infrastructure during its operation. With a large number of aging civil infrastructure and the growing problem of deterioration, there is an overwhelming amount of maintenance, repair, and replacement activities to be done. To address this, decision support methods have become paramount. This research proposes a mathematical tool that provides a rehabilitation program for transportation agencies while optimizing the selection of MRR strategies. The aim here is to maximize the performance of the asset or the infrastructure and minimize the cost of operating that infrastructure.
For this one, you need just
using the surface.
Looking at the literature review briefly, multi-objective models in bridge maintenance scheduling often aim to minimize both maintenance costs and traffic delays. For instance, a study by Mao et al. Proposed a bi-level programming model that minimizes traffic delays while maximizing the number of bridges to be inspected within considering budget constraints. Another approach developed by Cheney and Frangopoul introduces a framework utilizing multi-objective generic algorithms for preventative maintenance scheduling across the highway bridge network. Montazeri and Turan propose a reliability-based decision-making framework, emphasizing the importance of life cycle performance and maintenance costs. The challenge of maintaining the transportation networks have resulted promoting innovative decision systems. Transportation agencies have increased the private sector involvement through long-term warranty contracts or what's called performance-based contracts. The integration of innovative decision support model under performance-based contract settings has advanced the MRR strategies significantly. In my previous research, I designed a fuzzy-based framework for implementation performance-based contracts in bridge asset management. Implementing the framework enables contractors to execute various MRR strategies under different budget and performance requirements.
Stable flight and precise navigation in such kind of.
The automated decision-making support tool that I'm proposing here today, the framework itself, including the inputs, tools, and techniques, outputs are illustrated in the figure as you can see. The proposed tool considers bridge deck in particular because it deteriorates faster than any other component due to its direct exposure to traffic and also to the external environment factors such as salting. Here in North America, usually with the cold weather, salting during winter seasons will affect and make the bridge structure degrade quickly. The development of the automated tool involves two key components. First, modeling the performance of the bridge deck or the infrastructure, the targeted infrastructure, and second, optimizing the selection of MRR strategies.
Dynamic construction tasks.
Let's expand on the first key component, which is performance modeling. First, we need to start by evaluating current performance. Assessing the condition of the bridge is essential. To enhance the reliability of performance assessment, both surface and subsurface defects should be considered. So typically, the common method in order to analyze and assess the bridge condition will be through visual inspections. The bridge inspector will go and inspect the bridges, and he will try his best to find surface defects. The output of this process will be a report, and this is a sample report from an MTQ inspection report. Some of my research or previous work included integrating technology into this visual inspection. I've used in my research ground penetrating radar that can detect subsurface defect, specifically the potential of corrosion in RC concrete bridges for infrastructure. The output of that process after some scan and analysis will be a corrosive map as it's shown, and it will be rated using different category. In this research, I've aligned the criteria for grading with PQ, which is a 4 criteria, good, fair, poor, and critical.
So with this module,
to estimate element degradation over time, probabilistic or stochastic modeling are used. Given the bridge deterioration follow a stochastic nature, rather than deterministic process, the Weibull distribution function is frequently employed. So the automated tool embedding the Weibull distribution function as a deterioration or to forecast and project the future performance rates of the bridge.
So for the experiment, first we can.
And the third subcomponent I'll say is MRR modeling, which involves identifying appropriate MRR strategies, estimating resulting performance improvement, and calculating the costs with those associated type of strategy. It's worth noting that for the table I've used here, it can use the cost based on a percentage of the replacement cost value of the structure or the original cost after you can inflate it to current dollar. Or also you can use the unit rate based on the strategy that you have selected. And for each action unit cost, it includes the direct cost, indirect cost, and a markup to cover contractors' profit and contingency. And the table I'm showing here, it's in Canadian dollar, adjusting to 2024 value. The second key component is optimizing MRR strategies. As a modification to the well-known genetic algorithms, in this research, a modified GA is used due to its quick conversion and excellent performance. As in this modification, GA for each individual chromosome defines the potential MRR action over the planning years. The chromosomes are generated in a way to satisfy the budget constraints. The population is replaced with a new random chromosome in case of movement over several attempts during the planning years. This modified GA is developed using MATLAB and the optimization toolbox in the software.
Stable flight.
As a case study is discussed here as a proof of concept and illustration of the presented tool. The tool is applied to a bridge here in Quebec, the province of Quebec. An optimization scenario was carried over the initial remaining life cycle time of the bridge, which is till 2040, which is assuming the bridge life cycle will be 75 years. So it will be from the date of the study, 18 years from that till 2040. To run the tool, users must input the condition rating, construction year, a year of the last inspection from the latest inspection report, and the current year, the year that they are generating the scheduling plan. Additional input variables are required to execute the decision-making tool, such as the duration of the MRR plan, whether we are going to study it for 5 years, 10 years, 15 years, etc., and the interest rate. In my study, I used an interest rate of 4%, and the performance thresholds, how much we want to deteriorate, or what's the minimum threshold that we are going to have that we don't need to exceed the bridge. We don't want to reach to a failure state of the bridge because of the safety concerns for the users. The tool then automatically calculates the current performance utilizing its embedded deterioration function. Moreover, the MRR costs are incorporated based on the MRR modeling formulation as shown in the previous table. The figure here shows the performance without and with MRR interventions after applying the developed tool. It also provides the present work of the optimized scenario. And in this case, it was calculated to be a total of around $1.7 million over 18 years, again, to maintain the bridge based on the budget constraints that we have provided and based on the timeline
And
the
at the
study.
end, I would like to thank my lab mates.
To conclude my presentation, the majority of the existing decision-making methodologies are aiming to balance the dual objectives of maintaining the performance of infrastructure.
Okay, so thank you for
While
presentation.
maintaining the
Any
total cost.
question or
These conflicting
comment?
goals significantly complicate the decision-making process. To address this
Yes,
by
please.
objective optimization challenge, this research developed an automated decision-making tool for long-term scheduling of MRR strategies. However, this research do have some certain limitations. The first one is a study primarily focused on the bridge dig, where we can expand it to other elements like abutments or bridge walls. And also it can be expanded to other infrastructure like pavements, tunnels, etc. Second, the effect of MRR actions on bridge performance were restricted to maintenance, repair, and replacement. In other guidelines, in other provinces or the states, for example, they used minor rehabilitation or major rehabilitation where they enforce or increase the bridge dig with an additional steel and concrete. And the third is that the user and external costs, such as user delays associated with the MRR actions, are excluded, which can be incorporated in the future. Some of the future research is that to expand again to different bridge elements and different infrastructures. Additionally, future work could integrate real-time sensors data from structural health monitoring to dynamically update the deterioration models. Thank you so much for listening and for your attention and interest, and I will be happy to answer any questions. Thank you.